Okay, so we have our ammonia system, and what we would have is our normal refrigeration system. So we would have a case where we have a condenser to a metering device, to an evaporator. And so, as I said, we have a few systems that replace the compressor. Okay, so everything else in the system is the same, but what we have is a couple different vessels. Okay, and so what we end up, and we'll start maybe up here, what we've got is a mixture in here of water, which is one of the fluids that's required in this system, and then ammonia. And so I'll use green to represent my ammonia. So my green is my ammonia, and blue is my water, or H2O. Okay, so I've got a mixture of ammonia and water. Any ideas how I'm going to separate the ammonia from the water? I'm going to add some heat. Okay, so great. I'm going to add in some heat here. And I've got heat coming in. And what that's going to do is it's going to free up some of my ammonia. Okay, so my ammonia is going to vaporize. And what I have is vapor that makes its way to the rest of the refrigeration system. Okay, that's good, except for at some point, the ammonia and water that's contained in here is going to run out of ammonia. So, what I need to do is replenish it with ammonia. And so my ammonia comes back from my refrigeration process as a liquid, okay, and it makes its way back to my vessel here at the bottom. What's inside the bottom? Well, I got a few things. One, my mostly water returns down and enters back to that vessel. And my ammonia comes in. My green pen went. So ammonia comes in, and I want these guys to mix, and I want the ammonia to be absorbed. So what I do is I carry this guy through, and my liquid ammonia is going to be added into my system. Okay, so this guy's kind of coming in. And then as well, my water comes in, and he's going to get sprayed in. And hopefully at that point, what happens is I get some water, and it's going to mix with some ammonia. I have two different names for components here. Okay, so this guy up top, what is its job? It's going to separate the ammonia. Okay, and what I consider it to be called is the generator. Okay, so it's going to be generating ammonia. Okay, so this guy's my generator. And this guy, what he's doing is he's absorbing ammonia. So this guy is my absorber. Okay, so I have two different components there. Eventually, I get enough ammonia absorbed in here, and I want to return it back up. So what I have is a pathway where I add in a pump, and I pump back up. So I have a recirculation of fluid between my absorber and my generator, and what it allows me to do is carry my ammonia through and absorb it into the water here and then release it up top. Because of my pump, and then I've got a little metering device here, I have a high pressure side and I've got a low pressure side, just like I would inside of my refrigeration system. One final thing to add to my process, over time, because I'm adding in heat, it's going to get too hot. So I'll have another loop here, which I would use for cooling. I have a couple of other terms that I've included. I have what's known as strong aqua and weak aqua. Any idea where strong aqua would be? So strong aqua is going to be the one with the highest concentration of ammonia. Okay, so coming up from my absorber, making its way to the generator, is going to be my strong aqua. And then on the way down, where I have less ammonia, I'm going to have what's known as a weak aqua solution. Questions on this? Yeah.
How do you have liquid coming out of an evaporator?
Oh, thank you. No, should not be liquid. Should be vapor. Thank you. Thank you. Any other questions? Yeah, yes, sir. Yeah.
Why are we adding water to ammonia?
So the ammonia dissolves or absorbs into the water. Okay, so at different temperatures, they'll absorb at different rates. Okay, so at a low temperature, the ammonia will absorb fairly readily into the water. But if we increase the temperature like we are in the generator, then the ammonia essentially, we could think it like boils off, or it disassociates from the water, or that aqua mixture. So essentially the water acts as a carrier. In the bottom, the ammonia absorbs into the water, and then when it makes it up to the generator portion, then it is allowed with a bit of heat to boil off or vaporize out of that mixture. Okay, the water remains. It's not hot enough to vaporize the water, but it's hot enough to vaporize the ammonia. Okay, so when we talk about the concentration of ammonia, so the difference between the strong aqua and the weak aqua is how much ammonia we have inside of that water solution. So a strong solution would have a lot of ammonia, and a weak solution would have not very much ammonia. We can think of it kind of like it being concentrated or dilute, okay? Anyway, so strong aqua, lots of ammonia inside of it, okay? And I don't think we have a very huge difference in the concentrations, okay? These things are designed to replace the compressor, but it's hard with that process to allow a huge amount of ammonia to flow through those processes. They tend to run continuously, and they tend to run without as much flexibility as you would with a compressor system. Generally, this system, based on ammonia, we may be looking at an evaporator temperature, I don't know, maybe like minus 30 degrees Celsius would be sort of the operating condition for this. So used in a lot of freezer type applications because it can get quite cold. Yep.
First time I saw one of these.
Yep.
I was in a trailer.
Yes.
It had a pilot light.
Yep.
And there was no electricity.
Could be, yeah.
Froze ice cube in like half an hour.
So I believe in that case what happens is it would move from one space to the other based on density changes. Okay, so in a more industrial setting, we would use a pump to drive it. The pumps don't have as much electricity consumption as a compressor. They're just really moving from one spot to another. But yeah, in a case like this sort of style, you may see in like an RV or something like that, a little refrigerator, and you'll see it's kind of odd because you run the refrigeration with a small little flame. And you go like, how could this work? But that's the style of system that's inside of those RV fridges and freezers. They run with a small little flame input into the system, and that is enough to drive a little flow of ammonia through the rest of the refrigeration system. Yeah, so that's exactly where you'd see that kind of application potentially on a small scale. Yeah. Okay, I'm going to move on to our next style. Okay, so first of all, the full drawing that we produced is on the top of your next page there. Okay, so that's your textbook drawing, and I think we got all the parts, did we? Oh, good. Okay, I think I'm good. Okay, so our next absorption unit has water in it, okay? But what's different about this system is that now water is the refrigerant, okay? So before ammonia was the refrigerant, and in this case, water is the refrigerant, and then we have a substance, lithium bromide, LiBr, which is our carrier. And the thing that's interesting, I guess, about this system is the pressures. If we want to use water as a refrigerant, what do we got to do with temperature, or sorry, with our pressures? They got to be very low, okay? So especially if we want to do cooling, application of this might be cooling a building or something like that. So we may want 5 or 6 degree water as our end product. In order for us to have a phase change around 5 degrees, we have to have very low pressures, almost vacuum conditions. Okay, so these things operate at very low conditions. And in fact, where you'd be sitting is in your kind of your evaporator section. You know, you're going to be looking at somewhere around 1 kilopascal of pressure. So 1% of atmospheric pressure, somewhere in that range. And then your condenser is probably running around 45 degrees or something like that. So maybe 10 kPa would be some of the pressures that these systems sit at. So generally 5 to 45 would be sort of our temperature ranges, and our pressure ranges would be anywhere from, you know, 5 or 6 kPa, or sorry, 0.5 to 0.8 kPa, and then maybe 10 kPa on the high side. So very low pressures in terms of atmospheric conditions, but that's kind of the scheme for these things to work. Okay, so let's look at some components here. Let's start out by taking a look at our evaporator and our absorber. Okay, so first thing that happens is we have water, which is our refrigerant. Okay, so we got water vapor, which has left the evaporator. So we got vapor that's leaving. So let's take a look at what our evaporator may look like. So it's doing cooling with some process water here, and into our evaporator, we have some liquid, right? So what's entering into that system is going to be some liquid water. And often what we're going to do is just have a little pumping system so that we've got a pump and we'll have a little spray so that it sort of mists on top of the tubes that need to be cooled. And as these guys absorb heat, it's going to create some vapor, and so we have vapor that leaves. So water comes in, and we've got this lithium bromide solution, okay, that's sitting down here, and it's sitting down at the bottom, and so we need these guys to mix because I got this vapor that's sort of coming in. And so with our lithium bromide solution, again, we're going to have another little pump to pump this guy around, and he's going to spray in. And in doing so, what we should do is get a case where we've made a nice mix of water and this lithium bromide solution, so it absorbs some of the water that's coming in. Okay, and so that's how we trap the water that comes off of our evaporator, and we can contain it within that lithium bromide solution. So then the next thing that we have to do is we have to be able to up its pressure, and we have to be able to move it to a different vessel, and we need to be able to vaporize off that water that's now trapped inside of that solution. Okay, and so what we do is we've got another device. Here, which we'd consider to be our generator. Okay, so our generator, if it's going to drive off some vapor, generally what we're going to have is some mix of water and lithium bromide. Okay, so that came out of our absorber. And what we would generally do with that is we're going to pump it up. So this solution gets pumped, and we're going to send it up to our generator. So it comes up here, and it comes in. And that's sort of a mix, so I'll just show both. Okay, how did we drive off the ammonia in the last system? We added some heat. Okay, so this is where our heat input comes in. So we've got some heat that's coming in. And when it does that, it's going to drive off some water vapor, and that vapor goes to my condenser. Okay, and we'll complete the rest of the refrigeration cycle. What's left is we have a little bit of fluid that doesn't have as much water left in it, and we want to return it back to our absorber. So we've got another pathway that comes down, and he is going to end up feeding back into the absorber. Same as we did on the other, the absorber needs to get rid of heat. So we had heat that was added here. The absorber has to lose a bit of heat. So, so we got another heating and cooling pathway, and this time this guy is going to do some cooling. Because what comes out of here is hot, and what comes out of here is generally cool, we can add in a heat exchanger so that we have a heat exchanger, and the heat exchanger, what its job is when we've got the hot fluid or the warm fluid that leaves, it's going to give up some of its heat to the cold fluid that's moving up, and it needs to be heated. All right, so we've got a little heat exchanger in between. So similar process to our ammonia system with our absorber and our generator. The difference is really in this is we've got a couple other pumps. We've got a heat exchanger that often gets added in, and different fluids that are being used as we move through the system. But the same sort of principle holds. We've got an absorber that's bringing in the refrigerant and absorbing it, and then we have a generator that's allowing the refrigerant to leave. Sometimes we call the generator another term, which would be a concentrator. Okay. Meaning we're making this solution more concentrated. Okay. Concentrated meaning less water, which would mean that this solution is what we would consider to be dilute because it has water in it. Dilute's what we're trying to achieve, so careful of the terminology, because in this case dilute is a good thing, and concentrated is what we're trying to accomplish on the way down. Okay, so stop there. Any questions at this point? Any questions? All right, and there's my other sheet then. Okay. Okay, you've got a couple of sheets that I handed out. So the one, this is out of your textbooks. So this is your, this is the diagram we just created. Okay, condenser and evaporator. I didn't include. They're pretty much our standard condenser and evaporator systems. Okay. This is the generator and the absorber that we added in. And drew out our different process pathways for it. On the back side of this page, what they've done is they've taken this system and they've coupled the systems. So we know that there's a difference of pressure across the orifice and through the pumps. So we have a high and a low pressure system, okay? So everything on here is at high pressure, everything down here is low pressure. And so what they often do in these systems is they'll combine them all into one. So in this case, what we have is an absorber coupled with the evaporator. So instead of connect it by pipes as the vapor moves from the evaporator to the absorber, it's all contained within one vessel. Same thing up here between our condenser and our generator. It's all contained within one vessel. And the reason for that is often we have very low pressures in our systems, so we create one significantly sized pressure vessel which can hold the low pressures, as opposed to a whole bunch of different components in other vessels. Okay, so that's one reason why we've gone with this route. I'm not 100% sure if we've got time, but maybe we'll try it. So I have a blank one of these. And let's see if we can talk through how our systems are oriented to try to get to that final drawing. All right. This is a good challenge for us, I think. Good challenge for us. Okay. So the different systems down here, this is our evaporator and our absorber. And then up here is our condenser and our generator. Okay, we'll start at our evaporator. That's where we started the last time. So our evaporator is here. Okay, so this is our evaporator. And it has some water sitting in it. And what we're going to do with our evaporator is we want to have some heat exchange to our chilled water. And in order to do that, what we often do is going to spray it onto that, spray the water onto this surface. Okay, so we have a little pump that's going to drive it up. And we're going to do a little bit of spraying. And what that's going to allow us to do is create a little bit of vapor. Okay, so vapor is going to come off, and it's going to make its way down into this lower cavity. My lower cavity is going to contain, my lithium bromide solution. And in order to absorb the vapor, I got a pump that's going to pump up and spray some of my lithium bromide solution down. And when it does, hopefully the vapor that's in here should be able to be absorbed into that solution. This system, in the absorber, we do need some cooling water. So if I have a cooling water loop, it's going to come in, and I've got some cooling, and I'll bring that guy out over here. My absorbed solution is going to leave here. I got a pump to drive it, and he's going to make its way up to my generator. My generator is going to be heated with some of my available, hopefully, waste heat. And that's going to allow me to drive off some vapor. vapor's going to fill this cavity. And with a bit more cooling, I'm going to be able to condense some of my liquid or some of my vapor into liquid and create a reservoir of liquid water. My liquid water leaves my condenser and it can make its way into my lower vessel, which then gets sprayed in order to try to evaporate some of that vapor. We got one final thing, which is that over time, I'm going to get concentrated lithium bromide solution up at the top. And so we need to return him down. And he returns back to this vessel where he can pour in. Because it's a hot fluid up here and a cold fluid down here, and we're crossing paths, we have a heat exchanger that is added. My system, because it's water as my refrigerant, operates at low pressures. So generally my condenser is going to operate at the highest temperatures and pressures, and maybe we're somewhere around 45 degrees, and somewhere around maybe 10 kPa would be the pressure in the upper vessel. And my lower vessel probably sitting somewhere around, I don't know, 5 to 6 degrees, and maybe, I don't know, 0.8 kPa, something like that.
Absolute, right?
Yes, it is. Yeah. So that's absolute pressure. So pretty close to a vacuum. Nice system, eh? That's a lot of pathways and a lot of manipulation just to get rid of compressor work, okay? But the payoffs are there for a lot of systems, okay? So common in heating and cooling in commercial buildings and other places, hospitals or whatever. The key thing is that if you're able to replace the compressor work, you can do so by adding in heat, as long as you've got an equivalent amount of heat to add into the system. And ideally, it would be something that's wasted heat. And if this thing's operating at 45 degrees, you know, we need to have, let's say, 50 degree Celsius heat source or higher in order for this thing to run.
Commercial and industrial installations, would we expect to see the two of these things sort of packaged together in one giant unit, or are they separate entities, you know, one's on one side of it, one's in another, or something?
Yeah, these, you wouldn't really have necessarily a hybrid system, okay, where you've got a mechanical component and an absorption component, but you may have different units that are feeding the same system, right? Because what happens inside of here is our end goal is the chilled water, and so our chilled water really is just one big system running through the building, supplying cooling to air conditioning units and or industrial process. So our chilled system, really we could tie into it with any device anywhere. Okay, so it's not just one central spot where the heat has to be added in. So you may have a number of rooftop units and a continuous flow of cooling water through the building. And maybe some of your rooftop units are absorption units, and maybe some are mechanical refrigeration, compression refrigeration systems. Yeah. Any other questions? Okay, this stuff is complicated. Please have a watch through of this and make sure that you kind of understand what's happening inside of the systems. I'll put the blank sheets up on Blackboard, print out a few, and make sure that you can follow through and make the right connections in the right directions. Little bit of homework for you guys to do over the reading week.